Hey everyone, in this video, we're going to continue our work in section 8.3. So in this video, we're going to learn about a new test for convergence or divergence of a series. It's called the integral test. But before we look at that formal result, I want to set up this theorem by comparing our infinite series with an integral, because it's going to be important in the formal theorem. Okay, so what are we given here? In this illustration? Well, we are considering an infinite series of terms a sub n's, n equals 1 to infinity, and we're going to let a sub n equal the value of a function f at input n. And let's also assume that f is continuous, positive, and decreasing. So when we're in that situation, so if we rewrote the term and made it look like a function, and that function is continuous, positive, and decreasing, then we can talk about the following results. Okay, so I'm going to decorate these two pictures that I have here. So notice both of these images is a graph of f of x. So that means when I plug in 1 here, this output of my function is f of 1. So that's f of 1, but that's equal to a sub 1. And that's just because that's how we're creating f, is the function whose value at those integers are the terms in my series. Okay, so then at 2, here we're going to have a sub 2. At 3 here, we're going to have a sub 3. So what I can do is create rectangles here. So I'm going to create my first rectangle with the width of 1, height of a sub 1. So the area of this rectangle is actually a sub 1. Then we can continue. So at 2, the output here is a sub 2. So if I go over 1, the area here is a sub 2. And I can continue. A sub 3, a sub 4, a sub 5, a sub 6. Okay, so let's add up those areas together. We're going to assume we did this forever. So we have a sub 1 plus a sub 2 plus a sub 3 plus a sub 4, etc. So now how does that compare to the integral using our curve f from 1 to infinity? So I'm going to write out that integral. So the integral from 1 to infinity of f of x dx. So how does that compare? Which is larger? So if we draw that in here, we'll see that that function is always less than those rectangles. So the value of the integral is going to be smaller than, or maybe equal to, if we get, close enough approximation to that infinite series or that infinite sum. Okay, but we can do this illustration in a little different way. So rather than starting at A1 and moving to the right, we could have started here at A2 and then moved to the left. And so now this rectangle has an area of A2. Here we're up here at A3, has an area of A3, area of A4, an area of A5, A6, A7, etc. Okay, so let's go ahead and write out that sum. So A now sub 2 plus a sub 3 plus a sub 4 plus ... infinitely many terms. How does that compare to this integral of f of x from 1 to infinity? We see that all of those rectangles are within the curve. So if we compare that sum to this integral, that sum is actually going to be smaller than or equal to our integral. So here are two statements we can make about these two infinite sums and the value of an infinite or improper integral. Okay, but notice this second result here. I could just add a1 to both sides, and that inequality remains, right? I'm just adding a finite number to both sides and the inequality remains. So that means further that we have the same sum, a1, a2, adding forever, is also less than or equal to a1 plus the integral from 1 to infinity of f of x dx. So I want to refer back to these statements. So I'm going to call this statement here fact 1. It's a fact. We just showed it out in that illustration, and this result here, fact 2. So why are these comparisons helpful? Well, a couple things we can observe here. I'll use the same purple here. A couple things we can observe. So in this first situation, we have that our infinite series is larger than some improper integral. So if we know that this improper integral actually blows up or diverges, what does that mean about our infinite series? Well, it's larger or equal to infinity, so it must also blow up. Now, in this second fact, we have that our integral is larger than our series. So if we know that this improper integral goes to some number, converges to, say, L, then our infinite series is less than some finite number, L, which means it must also be finite. So we get two results here based on these two facts. And we can summarize those two facts in what's called the integral test. So let's go ahead and fill this in. So it says, suppose that f is continuous, positive, and decreasing. That's all important. We need all of these three things. And we need decreasing. Well, we need continuous and positive in order for us to write those improper integrals. And we need decreasing in order to have these comparisons that we just wrote. Okay, so if we have those on some interval, let's just start at c. In our example, we started at 1, but we can start at any c. And let the function value at n be the term of our sequence an, then we have the following results. So if the integral from c to infinity of f of x dx, if that diverges, so blows up, then what did we see happen? Well, then the series of an's diverges. And so that's using that fact 1. And that's just the reasoning that we just went through. And I'm just abbreviating here. We don't, when we're in the world of infinite series, we don't have to write the indices. It's known that what we're talking about is an infinite series where the terms go from n equals 1 to infinity. So we can write that shorthand. And then our second result is the following. If the integral from c to infinity of f of x dx converges, so it means goes to some value, finite value, then the infinite series also converges. And this is by fact 2. So it's worth stating here that if the integral blows up or goes to a limit, we don't know what the actual value of our series is. Well, in the case where we're in the first situation, then yes, we know our series also diverges, so it goes to infinity, or the value is infinity. But if our integral converges, then we know our series converges. We don't know what number it converges to. So then there's some more work to determine that. Awesome. So we're going to be using this integral test in future examples and questions to figure out the divergence or convergence of a series.